Okay, good morning to one and all. Last class, okay, due to some problems, we are not discussing properly regarding the RLC network. Okay, today we will see from starting onwards. Okay, once again, before starting the session, I am informing you that must and should you have to switch on the camera. Okay, for all the classes, not only for this class, for all the classes, for entire session, for 50 minutes, you have to switch on. Okay, if you switch off the camera, then we are going to play simply absent. Okay, we are that's fine. And next one also we have making some changes regarding your settings. You can't make your mic has unmute. Yeah. If you have any doubt in settings, you may find that in option more. Okay, you may find that raise hand. You know, if you have any doubt, you can raise the hand, or you can make a chat message to me. Okay, you can send a chat message. That means regarding the subject, if you have any doubt, you can send a message or you can raise the hand. Then I will make you unmute. Yeah, I will make you unmute. Then you can ask. Okay, that is rules and regulations regarding this Zoom application. From Monday onwards, these rules will be followed strictly. Okay, they will try to adjust for these rules. Okay, that's fine. Come to our class. uh, we are in the topic of RLC network. Okay, we had assumed that we had assumed a RLC network such that it may be in the R series and L and C are in parallel combination. L and C are parallel combination. We have considered an RLC network. For this type of network, if we apply a step response, if we apply a step signal, then what will be the output that we are going to see today class. Okay, if we apply a step response for an RLC network, then what will be the your output. Okay, that we are going to watch, that we are going to see in today's class. Okay, before going to step response, before going to see the step response, we are deriving the equation for this one. That means output equation. If you know the output equation, then whatever the input signal, we can draw the output waveforms. Okay, therefore, before deriving the response, before drawing the response, first I am interested to derive the output equation for this circuit. Okay, first I am deriving the output equation for this circuit. Okay, the output equation, how I am going to derive the output equation for this one means simple transfer function. Yeah, already you know that if we have a two elements like this, if we have a two elements like this, then simply you can find the transfer function. That is parallel branch divided by total impedance. Parallel branch. If suppose this is R2 and this is or R1, then transfer function is nothing but R2 divided by R1 plus R2. R2 divided by R1 plus R2. Okay, if we have like this only two elements, then we can find the transfer function. But here it is not in that form. Here in parallel we have one more element. In parallel we have one more element, which is a small difference from the standard circuit. Okay, therefore I am converting this one into our standard form. That is, I am making here a single element. Okay, in this here I am placing a single element. Simply that element is having the parallel impedance of this combination. Therefore, here I have taken the Laplace transform of your RLC network. That is R, Ls and 1 by Cs. The parallel combination of these two elements, parallel combination of L and C. That is nothing but a the R1, R2 divided by R1 plus R2. That is R1 is nothing but Ls. Okay, the impedance of inductance, impedance of capacitance. That is 1 by Cs divided by total impedance. That is Ls plus 1 by Cs. If you take the LCM, you may get this expression. If you take the LCM, you may get SL plus SL divided by 1 plus S square plus LC. Okay. Therefore, I am converting my RLC network into the standard form. Okay, this is my standard. I have only two elements now. Okay, I am having only two elements. If we have any element in series here, then it will be in standard form. Okay, then also it will be. That means we have seen the while deriving the transfer function, we have seen the two models for finding the transfer function. First one is like this. Okay, otherwise the second model will be like this. Okay, it will be in a mesh model. Okay, if it is in this form, we can find the transfer function directly, or otherwise if it is in this form, we can find out directly. Okay, but now our circuit is like this. Here we have the another element. Therefore, I had make this two in parallel combination to a single element. Okay, I had make it into a single element, and I have find it. I will make, wait a minute. I will make maximize. Okay. Uh, now you are able to see clearly. This is your parallel combination R1 into R2 divided by R1 plus R2. So that I had making these two into a single combination. And this is my equivalent impedance of these two elements. Okay, L and C equal impedance I had placed. Now it is in standard form. Therefore, directly I can write this transfer function. Directly I can write the transfer function. Okay, transfer function how you can write means the parallel branch divided by total impedance. Parallel branch divided by total impedance. Okay, parallel branch divided by total impedance, so that you may get the transfer function of this expression. For if you make a simplification, you may get this one. Okay, for this expression, I am for this expression, I am dividing with numerator denominator by RLC. Okay, why I am dividing with RLC means for simply to represent my transfer function in terms of damping factors. Okay, damping frequencies. To get that simplification, I am dividing the entire expression numerator and denominator by RLC element. Okay, if I make division, okay, if I divide it numerator by RLC, if I divide RLC, L get cancelled, you may get S into 1 by RC, S into 1 by RC, that is numerator. Denominator also each term by RLC. If this element is divided by RLC get cancelled, you may get S square. Okay, if this element is multiplied by RLC, LL get cancelled, you may get RC, 1 by RC. Okay, if it is multiplied by, you may get RR get cancelled, you may get LC. Okay, therefore numerator and denominator both are multiplied by RLC element. Okay, so that you may get this expression. Okay, now I am defining the two formulas which you already know. Okay, this damping frequency and the damping factor formulas which you have seen in your control system or your networks also you have seen. You may come across these formulas. Okay, therefore damping frequency omega naught is nothing but 1 by root LC. Okay, 1 by root LC. This is your damping frequency formula. Okay, where omega naught is nothing but 2 pi f. Omega naught is nothing but 2 pi f, where f is nothing but 1 by t. Therefore, that can be represented as 2 pi by t naught. That can be represented by 2 pi by t naught, where t naught is the damping frequency time period. Okay, t naught is the time period. If we represent it in terms of f, you may get the frequency. Therefore, 2 pi by t naught. Okay, where t naught is the time period. Okay, undamped frequency time period. Okay, therefore this can be written as t naught equal to 2 pi by root L. If you simply make t naught to this side, okay, 2 pi into root L, you make it. Okay, I will show you next slide. Okay, here I have mentioned our damping frequency, frequency time period, t naught equal to 2 pi into root LC. Okay, now I have defined the damping factor also. Damping factor K, it is going to represented by letter K, damping factor. These are the standard formulas. Okay, I think so. No need to derive these all things. You may come across in your transient analysis or in your control systems. Okay, time response. You may find these formulas. Okay, damping factor K is nothing but 1 by 2 pi root LC. These two are the standard formulas. One is omega naught, natural undamped frequency. Another one is damping factor K. Okay, these two are the standard formulas. Therefore, 1 by 2 R into root LC. Okay, now here in our transfer function we have 1 by RC. To get the 1 by RC, simply dividing the damping factor by damping time period, K by T naught. Okay, this is not pi, this is R. Okay, 2R. Okay, K is nothing but 1 by 2R into root LC. 1 by 2R into root LC into T naught. T naught is nothing but a 2 pi LC. Okay, 1 by 2 pi LC. Okay, therefore here L and L get cancelled. L and L get cancelled, so that you may get 4 pi root C into root C. You may get C. Okay, you may have the 4 pi into RC. 4 pi into RC you may have. If you take the 4 pi to this side, okay, if you take the 4 pi to this side, then you may get 1 by RC equal to 4 pi K by T naught. Okay, that I have right here. Okay, 1 by RC equal to 4 pi K by T naught. Okay, therefore this is your 1 by RC. Therefore, in our transfer function, we have the RC 1 by RC. We are going to replacing this 1 by RC in terms of 4 pi by k, 4 pi k by T naught. Okay, so that our transfer function we are going to get in terms of damping factors. We are going to get in terms of damping factors. Okay, that's why I had making about modifications. Why I have divided the numerator divided by RLC means simply to get my transfer function in terms of damping factors. Okay, because it is a second order. Simply we have the to another shortcut here. You can has the point came. I am saying another shortcut. Number of energy storing devices. Okay, by seeing that one, you can say the transfer function order. Okay, if you have a two energy storing devices, then you definitely are going to get second order system. Okay, second order system. If you have a single energy storage system, then you may have the first order system. That is the first order system. If we have a three element means we are going to get a third order. Okay, therefore, depending upon the energy storing devices, our transfer function is going to change. Okay, in our circuit we have two elements, L and C. Okay, those two are the energy storing devices. Therefore, definitely we are going to get the second order system. Second order system I am going to representing in terms of damping factor. Okay, therefore I have making those changes. That's why I have divided the my transfer function by RLC. Okay, and I have made a simplification so that I am going to get my standard transfer function. Okay, in this standard transfer function 1 by RC, I am going to substituting this 4 pi by T naught, 4 pi by T naught. Okay, so that now this is our standard transfer function. That is S into 4 pi by T naught divided by S square plus S into where 1 by RC may be replaced by 4 pi K by T naught. Okay, plus 1 by LC. Okay, 1 by LC now. Okay then. Okay, now we are going to taking it a characteristic equation. Okay, characteristic equation is nothing but already in control systems you have seen. Characteristic equation is nothing but a denominator equation. Denominator what you are going to having that equation we are going to call as an characteristic equation. Therefore, I have taken the characteristic equation. The characteristic is a second order function. Therefore, the second order function. Okay, the second order function it is a second order function. Therefore, I am going to having two roots. I am going to having the two roots. Let it be S1 and S2. The roots will be S1 comma S2. Okay, that's simply I have represent S1 1 comma 2. 1 comma 2 means we have two roots. That is S1 and S2. These two are the roots. Okay. Once you find out the roots, once you have find out the roots, then it can be further simplified. Okay, our transfer function can be further simplified as numerator will be as it is, that is S into 4 pi by T naught. Okay, numerator will be as it is. Denominator can be written as, if we have a roots S1 and S2, simply S1 plus S1. S plus S1 into S plus S2. Okay, simply the S1 and S2 are the roots. Therefore, the equation can be represented in terms of roots. Therefore, for this equation, if we multiply, this is the output by input. This is nothing but a output by input. Okay, now output equation is nothing but output equal to this equation into input, where input is the your step signal. Okay, that there in that way we are going to derive our expression. Okay, input in place of input voltage we are going to place the step voltage, so that for simplification we may get some by taking inverse Laplace transform we are going to get the equation in terms of time domain. By varying the time how the output voltage is going to vary, that we will derive finally. Okay, therefore for this equation directly to find the inverse Laplace transform means it is difficult. Okay, that's why I am going for the roots. I am taking the denominator expression and I have find out the roots. The roots is nothing but standard formula. I think so you know this formula. Minus b plus or minus root of b square minus 4ac by 2a. Okay, this is the equation for finding your roots. Okay, therefore here it may be in standard form a, and this will be your b, and this will be your c. Okay, if you substitute here, if you substitute this expression, and here you may get this expression, and it is further simplified. Okay, here we have a 4. 4 can be written as 2 square. 2 square can be taken inside. Okay, therefore 2 into 2 you may get 4. Square is nothing but a whole square you may get. Therefore 4 pi by T naught, 4 pi by T naught will be a common. Okay, therefore if you take it common, okay, only for this expression if you take it common, you may have under root 4 pi by T naught. 4 pi by T naught has common. 4 pi by T naught whole square has common means here you may have the k square term. k square minus, here it won't have any term, therefore k square minus 1. Okay, you may have this expression. Okay, if you take the 4 pi by t naught has common, 4 pi by t naught has common. If you take 4, this is under root. Okay, therefore the square and root get cancelled. This 4 pi by t naught will comes outside. Therefore this expression, this numerator term, this term can be represented as 4 pi by t naught into root of k square minus 1. Okay, yeah, if you take the minus as common inside, you may get 1 minus k square. If you take minus as common here, you may have the 1 minus k square. And root of minus 1, root of minus 1 is nothing but a minus j. I think so this also you know, root of minus 1, root of minus 1 is nothing but a your complex variable j. Okay, therefore this can be written as 4 minus 4 pi by 4 pi k by t naught plus or minus j into 4 pi by t naught root of 1 minus k square. I think so how you got this expression, which you may see in next slide. I have explained here. I think so you have understand how we got that expression. Okay, simply here see 4 pi by t naught, if I take common, you may get k square minus 1. If you take minus also common, you may get j. Okay, therefore j into 4 pi by t naught. Okay, 1 minus k you may get, 1 minus k square you may have. Okay, we will see next slide. Okay, see if we make the simplification, you make it like this: j into 4 pi by t naught into 1 minus k square, 1 minus k square. Okay, this is numerator term divided by 2. Okay, c value is 1. Okay, divided by 2. This is your a value, that is 4 pi by k naught into t naught. If you divide the entire expression by 2, you may get 2 pi. Okay, here also it 2 get cancelled, here also 2 will be cancelled, and here also 2 gets cancelled. Therefore 2 pi k by t naught plus or minus j into 2 pi by t naught into root of 1 minus k square. If you have a plus sign, okay, you may get s1. Okay, s1 equal to only plus sign here. S2 is nothing but a, you will have the minus sign here. Okay, if you place the minus sign, you will get one root. If you place the plus sign, you may get another root. Therefore, the roots of your denominator, okay, we may call it as a characteristic equation. Okay, technically we are going to call it as a characteristic equation. The roots of the characteristic equation, that is nothing but you have find out the S1 and S2. Therefore, our transfer function, that is V naught by Vi, can be represented as your numerator. You may have the 4 pi by t naught into s. This is your numerator, and denominator you may have the s plus. Okay, since it is a minus sign here, you have a minus sign here. If you have a minus sign, you may get the plus here. Okay, if you have a plus here, you may get minus here. Okay, for the both S1 and S2 will start with minus sign only. Okay, therefore here you may get S plus sign only. S plus S1. Okay, S plus S1 means minus minus sign will be minus of minus, you may get plus here. Okay, therefore 2 pi k by t naught plus j into 2 pi by t naught into root LC. That is S1. Okay, similarly into second one, that is S plus S2. S2 means simply you may have minus sign here. Okay, if you place minus sign here, you may have the S2. Okay, therefore this is your transfer function. Okay, now what are the second order system you have considered? The second order system, that is RLC network, we have find out the transfer function. Okay, if we find out the transfer function, that is output by input. Okay, now we will find out the response. Okay, if we apply the step response, how the system is going to be respond. For this type of system, if we give the step as the input, then how the output will be. Okay, that will be the output will be depends upon your damping factor. Okay, by changing the damping factor, the system may act as critically damped. I think so you have written these words also: critically damped, over damped, under damped. Okay, the whole system exhibit the different what we can say the response. Okay, system is going to give the different response for different damping factors. Okay, where k is nothing but a k is damping factor. K is nothing but we had seen the formula also, 1 by 2r into root LC. Okay, root L by C. Okay, 2r into root L by C. That means the parameters we have chosen. Okay, the R value, L value, and C value. The parameters we have chosen, depending on these parameters, that means RLC values. Okay, then depending on the parameters, you are going to get the output. If we choose the L value has the large value, we may get one response. Okay, if you choose the C value has large, we may get another response. If you choose the R value has large, we may get different response. That means depending upon these values, we are going to get the our output response. Okay. Therefore, depending on these values, the k value is going to be changed. Okay. If you set these values such that k value equal to 1, okay, that means we have chosen RLC. Okay, we have chosen some values. Okay, if we make this value such that this value equal to 1, then system is going to call as a critically dampened. Okay, that is our first case. When it is greater than 1, okay, when it is greater than 1, we are choosing these values such that the value is greater than 1, then we are going to call it as a over dampened. When it is less than 1, we are going to call it as an under dampened. Okay, therefore depending on the LNC values, this value can be greater than 1 or less than 1 or greater than 1. Okay, less than 1 or greater than 1. Okay, depending on this one, our system behavior is going to be changed. Okay, our system is going behavior is going to be changed. Therefore, we had derived the output expression also in terms of damping factors. That's why only we had taken our output expression in terms of K. Okay, we can keep it as the RLC also. Okay, if you keep these elements without modifying into K, then you may find the large transfer function, somewhat bigger transfer function. And analysis way, it will be somewhat difficult. Okay, analysis point, it may be difficult. That's why we have reduced it into damping factors. Okay, simply by depending upon the K value, the system response can be changed. Okay, that's why I have taken first one, that is K equal to 1. Okay, if my system having, I have chosen this RLC value such that K value is 1, then my system is a critically dampened system. Okay, I can say that my system is a critically dampened system. Okay, for a critically dampened system, if I apply the step signal, then what happens? Okay, what will be the output that we are going to see? Okay, for a critically dampened system, this K value has 1. Okay, if you put the K value has 1, this value goes to 0. Okay, this value will be goes to 0. If you place it here 1, therefore you may have the 2 pi by T naught. S1 equal to minus 2 pi by T naught. S2 is also minus 2 pi by T naught. Both are same. Therefore, we are getting the roots has equal and repeated, equal real roots. Otherwise, you can say that those are the real. Okay, the roots are real, equal, and repeated roots we have get. Okay, the imaginary part is 0. This is the imaginary part. Imaginary part is 0. The roots are real, equal, and repeated. Okay, otherwise in commutative bits they may form the bits like this also. For a critically dampened system, what will be the roots? Yeah, they may ask like this also. For a critically dampened system, the roots will be. Okay, how the roots will be? Roots will be real roots. Okay, roots will be real and equal or repeated. Both will give the same meaning. Okay, equal or repeated, both will use the same meaning. Okay, both are same. Okay, so that we can say that real repeated roots are real equal roots. Okay, we can say that instead of writing 2 times, we can use the both are same meaning. Okay, roots are real and repeated. Okay, roots are real and repeated. Okay, this, for a critical damper, they may ask, they can frame the bit. Okay, on this topic like this also, how the roots will be. Okay, for a undampered system, how the roots will be. For a over dampered system, how the roots will be. We will see one by one. Okay, like this, they may frame the bits. Okay, therefore, since they both are equal, we can write the S1 or S plus S1. Okay, into S plus S2. S1 and S2 are equal. Therefore, S plus A into S plus A. We can write S plus A whole square. Therefore, denominator is nothing but a numerator 4 pi by T naught into S. Denominator is nothing but S plus S1 into S plus S2. S1 and S2 are equal. Therefore, you may have the S plus S1 whole square. That is 2 pi by T naught, our root value. Okay, S plus 2 pi by T naught. Okay, for this expression, this is our output by input. If you take the input to this side, you may get the output equal to input into transfer function. Our input signal is step signal. Therefore, the Laplace transform of step. Okay, we know that step signal is nothing but a 1. Laplace transform is 1 by S. The Laplace transform of a step signal is 1 by S. If you are having the magnitude V, yeah, if 1 means that is unit step. If you take in 1 means that is unit step. Yeah, if you take the magnitude V means simply it is a step signal having the magnitude V. All our cases we are going to following the a step signal having the magnitude V. Okay, therefore we may have the our output Laplace transform of the input is nothing but a V by S. Okay, Laplace transform of input is nothing but a V by S. Okay, the step signal Laplace transform V by S. Here, therefore, output equal to input into our transfer function. Okay, therefore SS get cancelled. You may get, if you take V to this side, you may got V naught of S divided by V. The V is the input voltage equal to 4 pi by T naught into S plus 2 pi by T naught whole square. Here 4 pi by T naught is a constant. Therefore, you can write 1 plus S plus A whole square. S plus A whole square Laplace transform. Okay, because we are going to derive the, we are going to draw the output waveform in terms of time domain. And time domain means, since it is in frequency domain, where S is the frequency domain. Therefore, in order to convert into time domain, we will take the inverse Laplace transform. We will take the inverse Laplace transform. Here, inverse Laplace transform of S plus A whole square. Here I write the formula also. S plus A whole square. That is nothing but, if we have a square, that is multiplication by T. Okay, we may get multiplication by T. Therefore, T into e power minus AT. Okay. Therefore, this is also in the same form. Okay, this is also in the same form. Therefore, T into e power minus AT, where A is the 2 pi by T naught. Okay. Therefore, V naught by V, I may write in next slide. Okay. V naught by V, this V may take into this side. V naught by V equal to 4 pi by T naught into T into e power minus AT. Okay. Let I have taken a small assumption that T by T naught is nothing but a X. If we substitute that one, we may get 4 pi by, if we take the previous slide here. Okay. This T by T naught. T by T naught is nothing but a X. I have taken, the T is outside. Okay. T by T naught is nothing but a X. Therefore, 4 pi X into, here also, T by T naught. Okay. T by T naught is nothing but a X. Therefore, e power 2 pi X. Okay. If you take the assumption that if T by T naught equal to X, we may get in standard form. That is, the standard form, if you observe this one, this is a constant. This is a constant variable multiplied by some exponentially decreasing function. E power 80. Okay, e power 80 is minus 80. E power minus 80 is nothing but a exponentially decreasing one. Therefore, this is the exponentially decreasing quantity multiplied by a constant. Output by input. Therefore, this is V naught by V. I have taken V naught by V. Therefore, my y-axis is V naught by V, not V naught. Okay, y-axis is V naught by V. That's why if you multiply our step signal having the magnitude V, multiply by V, you may get the magnitude has 1. That's why I have mentioned here 1, not V. Okay. Therefore, our output signal is V naught by V. That is our y-axis. Y-axis is V naught by V, and having the step signal of magnitude 1. Having the magnitude 1. Actually, up to now we have taken the step signal as V. V divided by V, we make it as 1. Okay. That's why I have mentioned here 1, not V. Okay. Having the magnitude for that signal, this is the input signal. If you apply as an input, then you are going to get the output when this constant is dominating. When the constant value is dominating, your input to output may be increases. Output may be exponential increases. When this value gets domination, output gets decreases. Output gets decreases. Therefore, like that, okay, you may get slowly increasing and decreasing exponentially. Okay, exponentially increasing and decreasing function you are going to get at the output terminal. Okay, therefore, when you apply a step signal for an RLC network, if the RLC network is then critically damped, okay, the condition is K value equal to 1. Okay, then only you will get this type of shape. Okay, when the K value equal to 1, that means we have chosen R comma L comma C values such that 1 by 2R into root L by C. K or K formula. K formula is nothing but a 1 by 2R into root L by C. Okay, when this value goes to 1, okay, we have chosen RLC value such that, okay, then if we apply like this signal to the input signal, then we are going to get the output like this. Okay, therefore this is for critically damped system. Critically damped system. Case 2 is under damped system. For an under damped system, K value is less than 1. Okay, over damped means K value is greater than 1. Okay, when K value is less than, we will see the second case. Second case, our system is, we are going to choose these values, RLC values, such that K value is less than 1. Very, very important concept. Okay, this case 2, they may ask separately as a essay question. Okay, explain the RLC circuit under critical under damped system, or they may call it as a ringing circuit. Okay, we will continue in this topic only. Last topic, that is ringing circuit. Okay, when your circuit RLC network is going to act as a ringing circuit, like that they may frame the question. Okay, Therefore, case 2 is very, very important case. Okay, when the our k value is less than 1. Okay, when the k value is less than 1, we are going to call our system as an underdamped system. Okay, for underdamped system, if you apply a step signal, if you apply a step signal as the input, then we have to see the output, how the output will be. Before seeing the output, we will analyze the roots. Okay, since the k value is less than 1. Okay, this is less than 1. This is our root S1 and S2. Since it is less than 1, this value, okay, this value will be positive value. Under root we have a positive value, and which is not 0. Okay, therefore we can't neglect which is not 0. We may have this term. Okay, k value is less than 1. 1 minus smaller value, we may have a positive value. Positive value, and which is a which we can't make it a 0. Therefore we will get a roots as complex conjugate. Okay, when the k value is less than 1, how the roots will be? Roots are complex conjugate. Complex conjugate means x plus iy. Okay, if we have an x plus some jy or iy, okay, anything, and x minus iy, okay, simply sign will be changed. Okay, magnitude and phase are same. Therefore, this type of roots we are going to call as an complex roots. Okay, therefore, when your k value is less than 1, k value is less than 1, we are going to get a complex conjugate roots. We are going to get a complex conjugate root. Okay, simply remember this one. Therefore, our transfer function, we are going to, from the here onwards, we are going to see the transfer function, this one. Okay, which is somewhat lengthy. Therefore, simply I will mention it has S1 and it is has S2. Okay, instead of writing all this equation, simply here I may say that S plus S1, S plus S2. Okay, like that I will continue my explanation. Therefore, S1 is nothing but is 2 pi by k plus j into 2 pi by t naught into root of 1 minus k square. Similarly, if minus sign, you may get S2. Okay, this is your transfer function. Okay, for this transfer function, we have to first find out the output. Therefore, it has to be multiplied by your input signal V by S. Okay, if you take the input to this side, you may get output equal to input into this transfer function. Therefore, SS get cancelled, you may get V into. Therefore, this V will be taken this side. Therefore, output by V. Output by V equal to 4 pi by k by t naught divided by this expression we may have. Okay, we will go to next slide. Yeah, here I have written. Okay, my input signal is V by S. Therefore, output equal to V by S. SS get cancelled. You may have this term. Okay, for this one you have to take the inverse Laplace transform. Okay, for this expression you have to take the inverse Laplace transform. Already you know here I have written one or two steps for inverse Laplace for finding the inverse Laplace transform. We had first, before going inverse Laplace transform, we have to take the partial factors. Okay, we have to take the partial factors. That is a by our first function, b by our second, s plus s2. Okay, you in order to get the a, you have to substitute the s value this one. Okay, to make the b has 0. Okay, b 0 our energy, you can minus ochedi better. Okay, if you keep this one, then a value we may get has a value is this one. Okay, I have solved for a. Okay, the complex value కాబట్టి మీరు కన్ఫ్యూజ్ అవుతారు. ఏ వాల్యూ ఒకటి నేను సాల్వ్ చేసే. Okay, b value కూడా similarly అలాగే మీరు సాల్వ్ చేయొచ్చు. If you solve for b, you may get the b value has minus jk by the root of l by root of 1 minus t k square. Okay, we solve change also. Okay, you have to solve at your home. If you won't get these values, then inform me. I will solve it. Okay, therefore simply go for partial factors. Okay, this expression, for this expression you have to find out the inverse Laplace transform. Okay, for finding the inverse Laplace transform, we are going to take the Laplace partial factors for this one, and after taking the partial factors, we may take the inverse Laplace transform. Okay, therefore if we take the partial factors, we may get a and b values as common. Okay, therefore I have taken it as common, j by k into k by 1 minus k square. Okay, therefore the magnitude I have taken common. Therefore 1 by your s plus s1 minus b by s plus s2. Okay, if you take the inverse Laplace transform, you may get this is in the form of s plus a. S plus a is nothing but a e power minus 80. Okay, s plus a. Okay, where a is this one. Okay, this is your a. Okay, this is in the form of s plus a. If you take the inverse Laplace transform, you may get e power minus 80. Okay, minus e power minus at. Okay, you have get the e power minus at. Therefore, you have get the inverse Laplace transform for your function. Okay, from this expression, you have to remember this expression. Where s where this one is nothing but s1. We have get the e power minus s1 into t into e power minus s2 into t. Okay, these are the roots. Okay, these are the roots. Okay, therefore you have to remember this equation. From this equation, we are going to draw the output waveform. How the output waveform will be. Okay, as similar to previously, here also t by t naught we have taken as x. Okay, t by t naught will be taken as x, and we are making some simplification. And simplification here, you may get this form as e power j theta minus e power j theta by 2j. Like this, you may get the expression. Okay, which is nothing but a sine theta. Okay, therefore here you may see this, you can see here. Okay, this is the form of e power j theta minus j theta e power plus j theta. Here you may, this may be a minus. Okay, therefore minus j theta e power j theta. We don't have 2j denominator, we don't have 2j. Therefore this expression I am multiplying divided by 2j. Okay, I am multiplying divided by 2j. Therefore it will be in the standard form. It will be, therefore you here you get the 2j. Okay, therefore this j and j square you may get. J square is nothing but a minus 1. J square is already has seen. Root of minus 1 is nothing but a root of minus 1 is nothing but a j. Therefore if you square it both sides, j square is nothing but a minus 1. Okay, therefore here you denominator we don't have 2j. Therefore I am multiplying 2j and dividing 2j. Okay, therefore these, now it is in the standard form, e power j theta minus e power j theta. Okay, e power j theta minus e power j theta divided by 2j. Therefore this expression can be written as sine theta, where theta is this one. Okay, therefore theta is that one. Okay, and we get the 2j in before. Okay, 2j. Okay, we got the 2j. This j and j. Okay, j into j is nothing but j square. J square is nothing but minus 1. Therefore, this minus may goes to the positive. This minus may goes to the positive. Okay. Therefore, finally, you may get this j will be cancelled out. Yeah, this minus sign will be cancelled out. We may get 2k. 2k into 1 by 2k divided by root 1 minus k square into e power 2 pi by 2 pi k. T by t naught we can take in as x. Okay, t by t naught we are going to take in as x. Okay, into sine of 2 pi into t. Here also we may have the t. Okay, t by t naught we are going to take in as x. Okay, therefore 2 pi into root of 1 minus k square into x. Okay, like this we have get it. Okay, therefore if we observe this one, this is a constant value, this is an exponentially e power minus ax, yeah, 80. Okay, e power minus 80, exponentially decreasing function, and it is a sine function. Therefore if you see from last side, you may get the output as a sine wave. Okay, you are going to get a sine wave having a constant magnitude, and it will also exponentially decreases. Therefore your output will be having like a sine shape, and which is going to be decreased in its magnitude exponentially. After some time it may goes to the 1. Okay, I think so you have to understand. Okay, having constant magnitude and having a sinusoidal shape and having exponentially decreasing form. Okay, having the exponentially decreasing form. Therefore, the waveform starts like a sine wave. Waveform starts like a sine wave and having constant magnitudes and exponentially decreasing in its nature. Exponentially decreasing in nature and may reaches to the 1. Okay, and may reaches to the 1. Therefore, for a underdamped system, for an underdamped system, if we apply a step response, okay, for our circuit is nothing but this one. This is our circuit. Okay, for our circuit, if we apply a step signal and we have chosen this R value such that K value is less than 1. K value is less than 1. Okay, for this type of circuit, if we apply a step signal, then you are going to get the output in this form. Okay, sinusoidal signal which is exponentially decreasing in form. Okay, therefore finally it decreases. Finally it will be decreases. Okay, this is regarding your second case when K value is less than 1. Okay, by seeing this output expression, easily can do. Once you find out the transfer function, therefore directly you can take the output voltage. Output voltage equal to input into transfer function, where input is nothing but V by S. Okay, step voltage. And if you take the inverse Laplace transform for your input signal, then you may get the your standard form. Yeah, and I had made some small modifications. I had made which I converted into sine theta. Yeah, I had made small by using this formula. I had made some small modifications, and finally, by seeing this expression, I am going to write the my output waveform. I am going to write the output waveform. I think so. You are clear with this concept. Okay, why the shape of signal is exponentially decreasing, okay, due to this factor. Okay, due to this one, it will be in sinusoidal and it is having a constant magnitude. Okay, now we will see our last topic, which is continuation of your above topic, that is ringing circuit. Okay, they may ask for 2 marks bit also. Define ringing circuit. Okay, define ringing circuit. Here I have drawn the three waveforms for k value equal to 1. That is, this is your input signal. If suppose this is your input signal, when k value is equal to 1, k value equal to 1 means you may get a critically dampened system. Critically dampened system is it may slowly rises and slowly decreases exponentially. You can't say slowly, exponentially rises and exponentially decreases. When k value is greater than 1, okay, which we have seen not seen, we will see after. When k value is greater than 1, then output will be sharply rises. Very sharply it will rises and sharply it will be falls. Okay, we may get a peak. We are going to get a peak like this. We are going to get a sharp rise in our output waveform and sharp fall in our output waveform. Therefore, we are going to get like this. When k value is less than 1, we are getting a oscillations. We are getting the oscillations in the output signal, and these oscillations is going to be died after some time period. This oscillations is going to be died after some time period. Okay, for k value is 1, we are going to get exponential increasing and decreasing. For k value is greater than 1, a sharp rise. Okay, here I write when k value increases, the pulse amplitude increases. Okay, and becomes a narrow. Narrow means this one, a sharp rises and this width will be very small. Okay, that means if the k value, if I take k value has 2, okay, k value has 2 means I may get a pulse like this. Okay, when k value is 10, okay, the pulse rises very fastly and falls very fastly. Okay, this width is going to be reduced. We are going to get a narrow pulse. Okay, see here, compare these two pulses. Otherwise, I may write bigger here. When k value is greater than 1, you may get like this. If the k value further increases, we are going to get like this pulse. If it further increases, it may get like this. Okay, we are getting a short pulses at the input. Okay, when k value is, that will be k value equal to some 2, k value equal to some 10, k value equal to 100. Okay, as the k value is increasing, we are getting a narrow pulse at the input terminal, and finally it reaches to the 0. Okay, that's why I write the point as the k value increases, the pulse amplitude increases and becomes narrow. Narrow means this one. Okay, the width becomes narrow. Okay, this is for k greater than 1. Okay, now we are at the k is less than 1. Okay, we are discussing the k is less than 1. If the k is less than 1, we can say that it is a ringing circuit. Okay, why we are saying ringing means we are getting an oscillation. Okay, like a bell, we are getting the oscillations. Okay, therefore we can define the ringing circuit. Okay, we can define the ringing circuit such that RLC network, here I have write it. Okay, you can see here. Okay, I have write the definitions. Ringing circuit is defined as RLC circuit which is nearly gives the unoscillations. Okay, which are nearly RLC circuit which gives an undamped oscillations. Undamped oscillations means this oscillations should be goes to 0. Okay, an RLC circuit which is going to give the undamped oscillations. You should not get the these oscillations. Okay, it has to this oscillation has to be diode. Okay, that type of circuit we are going to call as an ringing circuit. Okay, ringing circuit is nothing but a RLC network which gives undamped oscillations. Okay, that is called ringing circuit. Okay, see this is an undamped oscillations. We are not getting the these oscillations. We are getting a constant magnitude. Okay, having the constant magnitude. We are having the, if our output is slowly reducing. Okay, damped out. Okay, our oscillations is damped out. We are going to say that it is damped out. Okay, therefore in our expression this one has to become an undamped oscillation. That means you have to maintain a constant sine wave. Okay, see the nature of the above equation is sine wave, which is exponentially decreasing. Okay, I have explained this one. For this one, we have a small derivation. Ringing circuit, we are deriving a quality factor. Okay, we have to derive the quality factor. How we are going to derive the quality factor means this is a standard form which you have seen for RLC network. Quality factor is 1 by 2k. Okay, 1 by 2k, and if we have a n cycles, we are getting n cycles at the output terminal. Okay, when the amplitude reduces to 1 by e times. Okay, when the amplitude reduces to 1 by e times, that means here you can see this here. This oscillations is going to be reduced and becomes the magnitude has 1 by e. Okay, at this point. Okay, at this point, it takes the n cycles. If this n cycles gets reduces, then we can say that it is a better ringing circuit. Okay, this oscillation should not be continued further. Okay, you should not take more n cycles. Okay, it has to be reduced. In order to reduce, what will be the your quality factor? That will be defined here by a simple example, that this value e power x1, due to this one we are getting exponentially decreased. When this value goes to the 0 or not 0, if it goes to 0 means entire value goes to 0. When this value equals to 1, when this value equals to 1, then we can eliminate these oscillations. Okay, simply we may get a sine having some constant magnitude, a sine function having some constant magnitude. Therefore this value has to be goes to the 1. Okay, how we are going to making this, that value will be goes to 1 means this numerator term has to goes to 1. Okay, therefore that we are substituting 2 pi k n equal to 1, 2 pi k n equal to 1. If we substitute, then from this we may get the q has, where 1 by 2 pi k is nothing but a q. Okay, 1 by 2k is nothing but a q. If we substitute that formula, you may get q equal to pi n. Okay, therefore that means here I write a small example also. If I said the quality factor has 12, quality factor q I have said quality factor has 12, then how many cycles after this damping magnitude reaches to e power 1 by or e power minus 1? E power minus 1 is nothing but 1 by e. 1 by e. Okay, when it reaches to 1 by e, then we can say that there is no this oscillation. This oscillations has been died out. Okay, 1 by e value is minimum. Okay, therefore after how many cycles we may get the magnitude has 1 by e. If we want to find out, we can use this one. When q is equal to 12, 12 by pi. Okay, where n is the number of cycles. 12 by pi is nothing but approximately we may get the 4. Therefore after 4 cycles, that means this is your first cycle, and this is your second cycle, and this is your third cycle, and this may be your fourth cycle. After a fourth cycle, the magnitude here, if you see the magnitude will be 1 by e. Okay, therefore by using this formula we can find out after how many cycles our magnitude will be reaches to 1 by e. Our magnitude will be reaches to 1 by e. That we can find out. That we can find out by using this formula. Okay, therefore the ringing circuit is nothing but it says a simple meaning, that is when the rings or oscillations magnitude reaches to 1 by e. When the oscillations or magnitude reaches to 1 by e, that period, that point, that type of circuit we are going to call as a ringing circuit. For an RLC circuit, undamped oscillations, that means we should not have the damping. That means we should not have this decreasing magnitude. Okay, we should not have this decreasing magnitude. If we have a decreasing magnitude, then automatically we are having the dampings. Okay, if we are having a constant magnitude, then we are saying that there is no dampings. Okay, therefore this is nothing but undamped system. Okay, in order to get a critically for an underdamped system, in order to get a undamped, this exponential term has to goes to 1. This exponential term has to goes to 1. Therefore, this exponential term we are equating to 1. Okay, we are equating to 1, and we are deriving the quality. Okay, quality factor q equal to pi n. This may be also an important formula. They may have framed the bits. Okay, I have explained a small example here. Here, at quality factor equal to 12. When quality factor equal to 12, after how many cycles you may get undamped system. Okay, after how many cycles you may get? After 4 cycles. After 4 cycles, simply 12 by pi. 12 by pi, approximately you may get 4. It may be 3.96, you may get it. Okay, approximately you can take it as 4. Okay, therefore after 4 cycles you are going to get a undamped system. Okay, After 4 cycles, it is undamped system. Yeah, I think so. We have completed our first chapter. Yeah, by at this point, I am stopping your unit one. Unit one has been completed, and I have shared this PPT. I have shared this PPT in our WhatsApp group also. Please download this PPT, and if possible, write in notes. Yeah, if you make the any xerox